app if you need French translation. All right, here's our agenda for today. Before I pass it off to Tim, we're going to pass it off to Tim for a land acknowledgement. Then each of our presenters will go through their project portion, starting with an overview, and then we'll talk about the regional climate model, and then we'll finish up with water flow and quality predictions and the implications for management. And then we'll finish with our Q&A. So obviously you folks don't have your microphones enabled. If you type your questions in the chat throughout the duration of the webinar, we'll be reading those questions at the end for about a half an hour. And with that, I'm going to pass it back to Tim, and we'll go ahead and get started. Thank you.
Just 1 second here. Okay. Good afternoon, everyone. My name is Tim Turriff, and I am one of your hosts for today's webinar. I am a Mohawk of Akwesasne, studying at the University of New Brunswick on the unceded and unsurrendered lands of the Wolastoq peoples. This territory is covered by the Treaties of Peace and Friendship, which the Wolastoq first signed with the British Crown in 1725. These treaties did not deal with the surrender of lands and resources, but in fact recognized Wolastoq title and established the rules for what was to be an ongoing relationship between nations. The main focus in today's webinar is on the Wolastoq. The Wolastoq has been the lifeline of the Mi'kmaq, Wolastoq, Passamaquoddy, Penobscot, and Abenaki peoples for time immemorial. We hope that this presentation can help you learn more about the science of the Wolastoq. While we understand that there is much more cultural and spiritual learning for us to do to better understand and appreciate the waters we know as the Wolastoq. So we have 3 parts to this research project that we're going to be talking about. The first part, Dr. Bourque and Dr. Shalaby have combined their efforts for part 1 of this research by refining and applying an existing landscape level water flow dynamics model of the upper Wolastoq Basin. And doing this, they have employed the regional climate model to create fully functional digital representations of day-to-day, present day, and future weather conditions and water flow dynamics in the upper Wolastoq. Dr. Qi has been responsible for part 2 of this project, which is focused on upscaling water quality indicators from small to large watersheds in the upper Wolastoq Basin. The result of this is a time series of water quality maps for the entire upper basin, the identification of high-risk zones of inferior water quality, and GIS maps of water quality in the upper Wolastoq system. The final part of this project is spearheaded by Ms. Reeder, who is also with us today. This part of the project is focused on increasing stakeholder awareness and transferring two-way knowledge to advance the understanding and address issues that affect the health of the Wolastoq. This will help stakeholders in defining common goals for integrating planning, remediation, and restoration efforts in the upper Wolastoq Basin. And now I will hand it over to my colleague, Max.
All right, thank you so much for attending our webinar today. We are so lucky to have with us this afternoon 3 amazing guest speakers to take us through the webinar. We have Dr. Charles Bourque joining us from the University of New Brunswick, who will be giving a project overview. We have Dr. Ahmad Shalaby, who's also affiliated with the University of New Brunswick, who will be covering the regional climate model. And then lastly, we have Dr. Junyu Qi from the University of Maryland, who is going to be covering water quality. So without further ado, Dr. Bourque, you're welcome to take control and start us off on our webinar today.
Okay, well, thank you. And before I start, I'd like to thank the moderators or the host of this webinar. Without their hard work, I wouldn't think that we would be able to provide this webinar today. So in terms of the project, the overall project is a 3-year project, and now we're in our 2nd year. And the title of the project is Water Quality and Incident Present Day and Future Water Flow Dynamics in the Upper Wolastoq Basin. And as indicated by the moderators, there are 3 parts, and part 1 deals with both looking at the water flow dynamics, both from an empirical point of view, but also from a modeling point of view. I will be dealing with the empirical aspect of the part 1, and then Dr. Shalaby will deal with looking at the results from a regional climate model. Then part 2 will be addressed by Dr. Qi. And just to let you know, there are more individuals involved with this particular project, in particular part 2. I'd like to name them. The first would be Dr. Fenyu Meng and Dr. Sheng Li from Agriculture Canada. And also, of course, the webinars being put on today because of Kim Reeder's efforts. So in terms of part 1, the title of the my section of the project relates to looking at the controls of springtime water flow dynamics in the Upper Wolastoq Basin. The information provided is actually written up in a paper. The actual project is very technically and very difficult probably to do in 20 minutes. And so what I'll be doing predominantly is really focusing to the results of the work opposed to the technical aspects. The paper that's mentioned in the background is being published in the Journal of Hydrology, so it has been peer reviewed, and so then there's associated confidence with what is being said today. So the problem relating to that first part 1 relates to the fact that the Wolastoq periodically floods. And so this is the particular problem that is the focus. Also, there's questions arise as to the role of land cover change on water flow and flooding dynamics in the river. So there's always been an issue about what if land cover change has an impact or not. In the scientific literature, it seems to have responses, if you want, in terms of sometimes it increases, other times it decreases it. So in terms of the Wolastoq, this is the particular question that's being addressed. Also, there's a role of transient climate. How does climate and climate change will have an impact, at least in the last 20 years or so, in the current historical point of view, but with the expectation, especially by using numerical models, we can look at that from a future point of view. So the objectives of this presentation is to characterize basin hydrological and water flow processes, including feedback. Another objective is to assess the impact of historical forest cover removal in the upper basin to springtime water flow dynamics, and that's during the period of 2001 to 2018. So here's the study area. Many of you are quite familiar with the placement of the upper Wolastoq River. Here is outlined in red. And in terms of some of the details, the larger watershed was subdivided into 4 different sub-watersheds where the study is being applied to each of those larger sub-watershed. The overall watershed area is in the vicinity of about 42,000 square kilometers. So it's quite a huge piece of real estate. The dots that you see here, the red ones, indicate virtual weather stations in a sense, based on the fact that there are very few weather stations that actually occur within some of these sub-watersheds. So to bypass that, we had to use existing data that is gridded or interpolated at about 1 kilometer resolution. The hydrographs or the hydrometric data is collected at the outlets of each of the watersheds, with the number associated with each of the hydrometric station is the actual upslope contributing area. So in terms of this assessment, because it's based on data, we had to amass a whole series of different data sets to get the information that is required to do this study that I'll describe the results of later. So as you can see, there's from the DAMET gridded data, which is NCAR product, but is available through the Oak Ridge National Laboratories archive, provides information at 1 kilometer, and from that we can extract the data at all of the virtual weather stations identified for the first watershed, but there will be corresponding virtual weather stations for the other sub-watersheds as well. The actual variables being used in the current analysis is the ones that are identified in orange. So not all of the variables are being used all at once. Another piece of information that was required is wind speed, because of the role of wind speed in terms of snowmelt. And that information comes from the Caribou Weather Station, which happens to be on the main side of the upper Wolastoq Basin. Also, we required the hydrometric data at the sub-catchment or the sub-watershed outlets, which typically incorporates discharge rate, and that comes from Environment Canada or Environment and Climate Change Canada. And of course, the last bit of information that was used relates to the forest cover loss, and that was based on Global Forest Watch Program data based on Landsat imagery from 2001 to 2018. So if we look at forests in northern New Brunswick, you can see that it's quite variable. Some in terms of vegetation regrowth, from bare ground conditions to slowly growing forests somewhere in the background of this image. So there's quite a variability in the level of forest conditions. So in terms of looking at the four watersheds or sub-watersheds, we have characterized the percent change over time. The box plots gives you the range of removal as a function of year, and the insect gives you the cumulative because of the legacy effect associated with cutting 1 year, also having an impact in the second year, and so forth. We will account for the cumulative change in the forest cover over time. And clearly, in terms of the four different sub-watershed, the smallest watershed, 01AH002, which is this one here, has the highest level of cutting, although the watershed is the smallest. In terms of the other two, the first watershed indicated here, and the second one, which is overlaps with the first one, we get about the same level of cutting per year. Of course, there's some variability indicated there, but overall, we get a pretty well even annual increment from 2001 to 2018. The least amount of cutting is being done in the third sub-watershed, or 01AG003. Now, to simplify the nomenclature, I'll just use, rather than using the complicated names, I'll simply call the first one sub-watershed 2, sub-watershed 3, and sub-watershed 4. And from all of other slides that are to come, they're ordered in the same fashion. So it's just to keep things simple. Now, in terms of the force cutting being done annually, we also need to account for the sort of the quasi-permanent cutting that has occurred over many decades maybe as the background. And here we have a force cover map that shows where fields are, agricultural fields, residential areas, water bodies, and so on and so forth. So this is sort of the base background data that is being used, where the percentage are indicated here in this inset table. So this will form the background variation in terms of force openings. So the key to the research is to do an examination of interaction among all the hydroclimatic and land cover variables that I've identified earlier. Now, to approach this empirical analysis, we take into account 3 different methods. These are statistical methods. Some of these methods may not be familiar with you, and that's okay. The paper does talk about these in more detail, but I won't spend too much in terms of the technical aspects of these methods. The only thing that you need to know with respect to these 3 methods is that the first method assumes linear causal relationships, while the other 2 deal with nonlinear relationships. And so we need to do that because some of the features of the system that we're considering has elements of nonlinearity as well as linear. And most times it's generally linear. Now, in terms of the first analysis, the rationale in using these different analyses is to see if different methods based on different assumptions can capture similar features within systems or not. And so the first approach is that we use the structural equation modeling approach. And based on that type of approach, and based on all of the information you have, we can come up with this path analysis, if you want, where the variables indicated here in a box symbol are actual variables that can be measured or have been measured based on the DAMET data or the Caribou information at the climate station. And so what we have here is that all of the variables in the boxes are measured, and the variables indicated in the circle are latent or unmeasured. The rationale in using unmeasured variables is that we know from our understanding of the system is that we know that meltwater production should be an element of the system. And as we indicate here, it does show that to be the case. The other latent variable indicated here is air, which represents air mass exchange. So as the air mass moves over the land, it starts to give off some of its properties as well as absorb some of the properties associated with land cover, but also variation in terrain. And this last latent variable is overland flow. So all of these together can give us a description of the system related to the the meteorological variables with respect to flow discharge rates in the Wolastoq River. In terms of the bottom variables, the first one here represents the flow rate. This one is the snow water equivalent, the day of year, and the precipitation. Up here is the snow degree day, the vapor pressure, partial vapor pressure of the air, which is part of the air mass, and the change in the temperature. And all of the areas you see here relate to the relationship between 2 variables. The solid blue lines represent positive direct relationships. The solid red lines represent negative direct relationships, and the dotted line here in this particular case only addresses the positive. Indirect effects. So what indirect effects means is that we know that there's an effect from one variable to another, and that indirect effect is that it passes through other variables that are unknown. But we know that according to what we see here, we know that there is a relationship between other variables that lead from, in this case, from meltwater production to the snow degree day accumulation or drop. Another one would be associated with overland flow. We know overland flow is quite complex, a lot of pathways, and so there's indirect relationship between overland flow and water discharge rates. One part of this diagram I'd like to show is that there's a linear feedback established between the snow degree days, meltwater production, and snow water equivalent. This snow water equivalent is the on-the-ground accumulation of snow, and it is represented as a quantity of water. Generally, this model, as indicated here, is that it does actually model the data rather well. So the data does confirm this understanding of the meltwater system in the upper Wolastoq Basin. The next approach was to look at a machine learning approach called extreme gradient boosting. It's very similar to random forest. Some of you are familiar with random forest. Extreme gradient boosting is out there, and it's a pretty powerful tool to use, especially with very nonlinear relationships. So here we have an output of the extreme gradient boosting for the stage height of the river at the, I think was at Edmundston, and shows that generally the approach can give very good results. Here we have the distribution of predictive versus observed using the model that was created with the input data that we mentioned earlier. Associated with that model development or training is that outputs the relative importance of different factors or variables that are, in this case, being considered that they might be related to water flow changes due to the spring snowmelt period. The greatest change or the greatest importance relates to the snow degree days, and you get a corresponding decrease in the snow water equivalent and cumulative force loss. And we see that there's almost an exponential decay. And we see that there's a slight increase with vapor pressure, meaning vapor pressure is important, but not as important as snow degree days. And where precipitation, here precipitation is in terms of rain, not snow. And we see that the relationship with respect to rain during the snowmelt period, it does happen, but it's not a common thing over the 17-year period being considered. The next approach is called convergent cross mapping. This particular method was developed through the theory associated with nonlinear dynamics within systems. And this is a convenient way to actually determine cause and effect relationships. And those relationships may actually be linear or nonlinear. So here we have a table that shows the various values according to this would be the p-value in terms of the first box. The boxes are there to focus your eyes to this particular information and the information at the end of the table. And so what was done is that I compared the snow degree day as it changed over time as a function of the discharge rates over time. So you have these two time series. And we look at the relationships between those situations where A to B, meaning A represents snow degree days and B is the discharge rate. And we also look at the opposite direction, the effect of B on A. And so we can actually determine if the level of causality is unidirectional or bidirectional. And so in terms of snow degree day, we see that it's actually bidirectional. Thus, for causality, we give a category of 3. So there's presence of bidirectional causality. That means the two variables actually affect each other. And that is a form of feedback. And we do the same thing for snow water equivalent. And we see again that there's this feedback. Again, labeled as presence of bidirectional causality. And this relates very much to that feedback that we saw in the structural equation model. We see it again, and that suggests that that relationship is linear. In terms of cumulative force loss, we see that it's only unidirectional. And that makes sense because if it's unidirectional, it means that the cumulative force loss has an impact on discharge rates, but discharge rates does not have an impact on force loss, which makes sense, right? And so the method actually picks that up. And thus the labeling of causality for the cumulative force loss as unidirectional. Then we go down to partial vapor pressure, and again we see a unidirectional causality. So that means water vapor in the air will condense once in contact with the cold snow, will condense, release latent heat, and cause melting. So here's a depiction of this convergent cross mapping. I won't go into the detail, but one of the elements of the method is that you get convergence in this predictive curve. The predictive curve, the x-axis is the level of the record length, and the y-axis is the Pearson's correlation coefficient. And whenever you see convergence, it suggests that that along with the p-value being lower than 0.05, there's an indication that there is a relationship. So the black line represents A forces B, and the red line indicates B forces A. And we see that the p-value for this set of variables, we see the p-value being larger than 0.05, and therefore the association B forces A does not occur, is not realistic, and therefore what you get is simply A forces B, which relates to the cumulative force loss to the variation in water discharge. Now, if we look at B, we actually have two different, the same, B is the same variable as above, but the only difference is A is the snow degree days, and we see that there's convergence in both cases, and the p-values are below 0.05, and so that means both are valid, and therefore associated with that, it coincides with the SEM model, and thus there's feedback associated with those two variables. So in terms of the this particular table, is simply looking at the different watersheds, sub-watersheds, and simply looking at the range of annual force cover loss as we go from 2001 to 2018. And initially, the amount of force cover loss, not taking into account the background conversion of force, but initially during the early 2000s, 2001, 2003, and so on, we see that the signal to noise ratio is small, and therefore we can't pick up that relationship. But as we increase the amount of cumulative force loss to larger values beyond, in this case, beyond 3%, 4%, we start to capture that signal. And so this is the case for all of the sub-watershed being considered here. The only watershed we don't see any impact at all relating the force cover to water discharge rates is the third watershed, where there's less than 1% extracted over the 17 years. And so the noise to signal ratio is such that we just can't pick up the signal, and therefore we can easily label that as absence of causality. Now, what we do here is really to test this scenario where land use versus no land use is being done to actually determine if in fact land use has an impact. And again, this method is used by or is looked at from a extreme gradient boosting approach, where the first scenario relates to no cutting at all, and the second one, there's an accumulative repeated cutting, annual cutting, where you get an increase in percent cut over the 17 years. And so what we see is that when we compare the two, we see that the cutting has increased over the 17 years, caused an increase of 32%. In terms of the second sub-watershed, we see that it's 13%, 11% for the for the third one, and for the smaller one, we still we see about a 13% increase based on the two force cover scenarios from no to the actual force cover removal. Now, we need to account for the fact that climate induces a certain level of trends. And what we see is that the peak snow cover over the last 41 years is that there has been hotspots where there's actually an accumulation of on-the-ground snow water equivalent. In terms of this watershed, we see this red spot. That red spot is statistically significant. And if we go across the watershed, we see again a statistically significant. If you look at the range, the p-value, they go from 0 to 1. Of course, the p-value of interest is at 0.05. And based on the 0.05 threshold, this region here does indicate a decrease in the snow water equivalent. So that means because there's an increase in snow water equivalent, 2008 is an example of that, with 1.6 meters of snow accumulated in the upper part of the watershed. We see that this potentially, for that first watershed, that we can see a dramatic increase in the discharge rate at the outlet of that watershed. Now, when we look at the second watershed, which encompasses this first watershed, this particular zone mitigates to some extent the increase that we see on the western side of the basin. All other values we see here, as you can see, the colors vary. All of these values are not statistically significant, but these two, this hot spot and cold spot, do show as being statistically significant. Now, if we look at the actual interseasonal stream flow rate change, this is over the 17-year period, we see that all outlets had an increase in stream discharge, all of them, except the third sub-watershed. The statistical significance is not there with 0.06 compared to 0.05. So this is not statistically significant. Now, this particular column to the right indicates the difference between what we calculated based on actual force cutting or force removal and no force removal. And what we see is that there's a tendency to increase with time, and all of them are statistically significant. So that means by more cutting and the cutting we do in 1 year compounds the cutting in the previous year and so on and so forth, because of that legacy effect, which may last for 15 to 20 years, in some cases up to 30 years, that compounding effect has an impact on water flow as we go from 2001 to 2018. Here is work that Dr. Shalaby will talk about, which is based strictly on a different approach completely, and he is showing the same thing. So this is for 2008, where the red line shows the control, no cutting, and the blue line shows that he's using the current cutting based on the global force watch data. And he sees that for 2008, it caused a 27% increase. Now in 2018, because there's more cutting being done from 2008 to 2018, we see that increased by 55%. So the more removal, the more the stream discharge will increase. And this is consistent to that last column that I've shown you. So two different approaches, yet they show pretty well the same thing. We are continuing to look at that because we want to make sure that the work is actually correct across all methods that we're going to be considering. The next step is to use a process-based model at the watershed level and see what the results might be. The resolution of the work done by Dr. Shalaby is somewhat coarse compared to the resolution that we use for the DAMIT data, but also the resolution that we'll get with a process-based hydrological model. And so that's it for my part of the presentation.
Thank you so much, Dr. Bourque. We're now going to hand off our presentation to Dr. Ahmad Shalaby so he can go through his portion of the presentation. You're good to take control, Dr. Shalaby.
Do you hear me?
Yeah, we can hear you.
Okay. Good afternoon, everyone. I am honored and pleased to be invited to the Maritime Climate Modeling and Upper St. John River Water Assessment webinar. In spring 2008, Wolastoq Basin witnessed a severe flood. Its likelihood is 35 years. The estimated property and business damages is around 23 million Canadian dollars. The large portion of the downtown Fredericton city is inundated by the river overflow. In spring 2012 was not severe downstream, but upstream, where Bourque and handover is severely affected. In spring 2018, we hit again by a 35-year flood as in 2008. The multiple occurrence of a rare event in a course of 10 years raises the question about the impact of climate change on the increasing frequency of severe phenomena and raises the question of man-made influence on the course of nature. This presentation tried to show the capability of the regional climate model to justify a main hypothesis that the annual forest removal activities in the upper Wolastoq Basin affect to a significant level the hydroclimatic process that causes spring floods. This will add an extra piece of evidence to the framework done by Professor Charles. At the
Dr.
beginning,
Shalaby,
yes?
would you be able to speak a little louder? The interpreter's having a hard time making out everything you're saying.
Okay.
Thank you.
Shall I start from the beginning or just from now, from here?
No, you can start from where you are now. Thank you.
Okay. At the beginning, I started by an introduction to the regional climate model, and then a brief history of the forest clear-cut activities in the upper Wolastoq Basin. After that, we will see how we can design a numerical experiment that simulates this anthropogenic factor. Finally, I will show the simulation results, hope to come up with a justifiable approach to this life-threatening problem. To know what is the regional climate model, we first introduce the global climate model. Theoretically, the global climate model is the application of Navier-Stokes equation. Navier-Stokes equations describe the basic conservation laws of any fluid in the universe, which are the conservation of momentum, conservation of energy, conservation of mass. These equations are written in a sense that reflect the atmospheric variables as atmospheric pressure, temperature, wind, and water vapor. The new set is what we call the atmospheric model, or we write them for ocean to have an ocean model. The coupled ocean atmospheric global model has sub-models: ocean model, land surface model, and atmospheric model. This coupled ocean atmospheric model is what we call global climate model. As you see, the coupled ocean atmospheric model includes complex processes such as cloud formation, chemistry, hydrological processes, and ocean atmosphere interactions fluxes. The anthropogenic emission from industry, agriculture activities, and transportation change the chemistry of the atmosphere, ocean, and land. These influences are included in the advanced global climate models. So the atmospheric model, So the atmospheric model eventually is a software written usually by Fortran programming language, and it is the implementation of the theoretical model on the expensive, massive, high-performance computers, which is not available for individual researcher or small research institutes. The regional climate model, on the other hand, is a magnifying lens that resolve physical processes that are not seen by the global model, such as lake effect, mountain weather, and detailed surface hydrology. The regional climate model becomes an attractive tool to study regional and local climates because it is efficient and doesn't need supercomputers. It is user-friendly, and by increasing the model resolution, we will resolve more processes and increase simulation accuracy. How do we apply the regional climate model? We dissect the 3D space vertically and horizontally to come up with boxes that covers the region under consideration, and then derive its initial and lateral boundary conditions from a global climate models by interpolation. Finally, we provide the topography, land cover data, and ocean temperature of our region of interest. The most developed regional climate model is an Earth system model that has many components that represent biogeochemical processes and land, cryosphere, ocean, atmosphere interactions. Now we come to the simulation design. The simulation domain must be greater than the domain of interest, which is the Wolastoq in our case. This is important to take in account the incoming wind and temperature from the lateral boundaries that influence the basin. The simulation domain is 200 times 200 grid cells in horizontal with 5 kilometer resolution and 18 layers in vertical. The simulation period is from 2007 up to 2019. We first validate the model climate simulation against observation. The model accurately simulates temperature annual cycle and precipitation annual cycle for St. Stephen Station in this graph. However, the model doesn't always have a very good job like this. The model is not so accurate to simulate precipitation cycle over Predictive, for example. Still, it has overestimation in winter season. The data from the Global Forest Watch program shows that the forest cover removal is linearly progressive in the upper Wolastoq. Some basins had lost up to 25% of its forest cover in less than 20 years. How do we prepare the model to simulate the impact of forest removal? In fact, the original land cover data set doesn't include forest loss. It is based on mid-90s land survey. The control or the reference simulation based on this dataset. For 2008, the upper basin forest land cover in red here is replaced by cropland in blue. By the percentage indicated in the above data, it is about 5% of the total area. For 2018, the upper basin forest land cover is replaced by cropland covered by about 20% of the total area. This reflects the progressive nature of the forest removal activities. We run the model twice and estimate the change for each year. Now, this figure shows the difference between land coverage change simulation and the control simulation of the snow melt for 2008 and 2018. It shows that progressive forest removal induces more snow melt from 2008 to 2018. To understand this, we refer to water balance, where evapotranspiration flux is partitioned between the forest canopy and understory. Forest canopy flux is mainly the canopy evapotranspiration. Understory flux is the sum of soil evaporation and ground snowpack sublimation. Forest removal disturbs the water balance such that decreasing forest canopy reduces the evapotranspiration flux, which results in increasing in snowpack. The surface runoff is a product of a snowmelt and the proxy for flood, as we know. The regional climate model predicts the increase in surface runoff in case of progressive clear cut. And as Professor Charles showed previously, the cumulative surface runoff for the upper Wolastoq Basin increases due to forest cover removal in both years in 2008 and 2018. However, it is evident that the difference increases from 2008 to 2018. We can conclude that the progressive forest removal will increase the likelihood of severe flood in the upper Wolastoq Basin. These results add a positive justification to what Professor Charles just analyzed. Thank you for listening.
Thank you so much, Dr. Ahmed Shalaby. We're now going to hand off the presentation to Dr. Junyu Qi. Dr. Qi, you're good to take control of the presentation.
Okay. Okay, can you hear me now?
Yes, we can hear you.
Okay. Good afternoon, everyone. My name is Junyu Qi. I'm a research scientist at the University of Maryland. It's my pleasure to be invited to this seminar and serving as one of the speakers. First, please allow me to introduce myself. I earned my PhD degree in hydrology and water resource management at UNB in 2017. And after that, I came to the University of Maryland as a postdoc. Later on, I became a research scientist to study water resource management and environmental modeling. So that's my short bio. Today, I'm going to talk about what I have done during my UNB years and what I'm doing in the Upper St. John River project. So the title of the presentation is decision making in water resources management from field to small and large watershed. So in this talk, I will first introduce the water resource problem as well as the best management practices to address them. Then I will talk about the two common methods to evaluate the impact of best management practices. Next, I would like to talk about the developing decision support system and its application in New Brunswick, and then the conclusion. As we know that freshwater resources are facing great challenges due to disturbances of human activities and climate change. Rising temperatures are causing more unpredictable weather and extreme weather events, leading to severe floods and droughts. Globally, about 70% of the fresh water is used for agriculture. As a result, non-pond source pollution has been degrading water quality caused by excessive inputs of chemical pollutants and soil erosion. To address water resources problems caused by agricultural activities, best management practices are widely promoted and used. These practices can be used to prevent soil erosion, reduce nutrient losses, conserve soil water, and sustain land productivity. However, when it comes to decision makers and stakeholders, the questions are how effective those BMPs are and where they should be implemented in the field. In other words, decision makers and stakeholders need data to judge whether they want to adopt certain BMPs. So one way to provide data is through field experiments. Basically, we can design and implement field experiments to see how effective the BMPs are. However, we can only conduct limited field experiments because they are expensive and time-consuming. Another problem is that the results derived from experiments are not easily transferable to other study areas, and the results cannot be validated. Another method is to use physically based distributed hydrologic model to evaluate the BMP's effects at the field or watershed scale. The benefits of using models are obvious. For example, they can fill data gap of experiments, they can provide accurate results, and they can predict future scenarios. As a result, they are widely received as decision support tools. However, models are not without problems, especially for decision makers and stakeholders who are not experts in models. For them, the model is not flexible and requires a complicated procedure and a long data processing time. In fact, what they need is an easy-to-use tool. So we thought a decision support system which takes advantage of strengths from post-field experiments and hydrological models would be a better option for decision makers. To realize that, we developed a decision support system based on the concept of decision rules, which are used to predict water quantity and quality on a grid scale level. The decision rules can be developed not only based on experiments and models, but also based on expert knowledge. So how do we develop decision rules? The basic idea is that we use regression models to develop relationships between a bunch of predictors and targeted water variables, such as stream flow, nitrate loading. The data needed for decision rules are derived from either experiments or model simulations. Of course, we can also put expert knowledge into the mix. Aside from regression models, there are lots of new methods that can be used to build relationships between predictors and water variables, such as machine learning, which in fact is used in this Upper St. John River project. So let's talk about what I have done to develop a decision support system. Recall that we need a hydrological model to fill the data gap of field experiment, right? So the model I was using is the SWAT model, which is one of the mostly used distributed watershed model to simulate water quantity and quality. It is developed by the USDA with purpose to simulate water quantity and quality as affected by land use and climate change in engaged watershed. One advantage of the model is that it has lots of management options which are needed for the development of a decision support system. So before we use the SWAT model to generate datasets needed for the development of decision rules, we need to make sure that the model can provide credible simulations. In other words, we need to calibrate and validate the SWAT model. To do that, we selected the Bourque watershed, a small experimental watershed with abundant monitored water data. Notice that the Bourque watershed is a sub-basin of a larger watershed, the Little River watershed, which will be used as a test bed for the decision support system. Also, the Little River watershed is also one small sub-watershed in the Upper St. John River Basin. So what we can see here is that using the decision support system, we can upscale results from field experiments and small watershed to larger basins. This is one of the advantages of the decision support system compared with other methods. So I will skip the complicated processes of model calibration and validation. After we got a well-calibrated SWAT model, we proceeded to conduct multiple BMP scenarios and generated simulations at the hydrological response unit were used to develop decision rules. With the help of ArcGIS, we can simulate water quantity and quality as affected by BMPs and land use change at a larger watershed scale. One important step before using the decision support system is to evaluate its performance at a larger watershed. Here it is Little River watershed. To do that, we compared the model simulations between the decision support system and the two versions of SWAT model. One is calibrated, another one is not calibrated. Here, I will not go into the details of the results. In general, the comparison results show that the performance of the decision support system in simulations of water quantity and quality were comparable to those of the calibrated SWAT model at the Little River watershed, and much better than the uncalibrated SWAT model. What this means is that the decision support system can replace the SWAT model to predict water resources at larger scales. So for the conclusion, in my study, I developed a decision support system to assess the impacts of land use change and the BMPs on water quantity and the quality for larger watershed in New Brunswick. For this Upper St. John River project, we are adopting the similar approach to develop a decision support system. The difference is that we will develop decision rules using machine learning techniques. Furthermore, we will consider more BMPs and include more input data. An ArcGIS-based interface will also be developed for decision makers to use. Thank you for your listening.
Thank you so much, Dr. Qi, and also to Dr. Bourque and Dr. Shalaby for presenting today, and all other researchers and stakeholders that have played a role in this research project. We would like to invite everyone in the audience, if you have any questions, please ask them by typing them into the chat feature. So that's the little chat bubble. And we will go through them with the research team. So we will be translating any French questions into English, and the answers will also be in English in order to make things as simple as possible for combining the recording of this webinar with the French translations. Just a couple more notes. We hope to send out a survey by the end of the week to measure the success of this webinar, so please keep an eye out for that. As well, for those who have expressed interest in obtaining a recording of this webinar, we will be working with the interpreters to create a combined French and English version, and we'll be making that available in the near future. So again, if anyone has questions, feel free to put them in the chat feature. Okay, so we have a couple of questions in these chats. So the first question is the DSS available for use and can it be shared?
Yeah. For the DSS, we are developing the first stage right now. For the second stage, which we will have a user interface add by the ArcGIS. That's what we are doing now. But actually, if you want to use a decision support system, you can use it. But but you need to have a guidance from us and a procedure you need to know in order to use that. But I would wait for the user interface for you to use. Yeah.
Thank you, Dr. Qi.
Yeah.
The next question is, could you outline the next steps for the overall project?
Okay, I think I'll address that. I noticed it was from James, my friend James at U of T. Yeah, the project, as indicated, is a 3-year project. We're now in the almost at the end of the second year. There has been a lot done with respect to generating the regional climate model for both historical, which we use as a reference, and also for the future from 2020 to 2000 to 2100. So 100 years of future conditions. So all of that has been done. It's sitting in high capacity drives that we have here at the university. And the next step for me is to start using that climate data, both historical model with regional climate model and for the future, to look at how the predictions should come out with future climate change. I'm spending time looking at the sensitivity of a hydrological model is different than the SWAT model that Dr. Qi talked about, but it does similar things, except it doesn't deal with the water quality part of the equation. So this is what we envision, is that we will continue and come up with spatial or maps of how based on land use and simulated land use, how we can what will we get with future climate change. And Dr. Qi and his graduate student, as well as Dr. Meng and Dr. Li, are working hard with respect to the dealing with the water quality aspect of the project. So hopefully there'll be a merging of results from the water flow characterization to the water quality element of the project eventually.
Thank you. The next question is from Marika Chaplin. I work for a sub-watershed outside the study boundary, Nashwauk. Many residents point their fingers at deforestation contributing to flooding. What is your message to the general public who live further downstream?
I guess I'll deal with this issue. The message I get from what I, from the study is that with the greater deforestation, there is a potential for, greater flooding. And we have to keep in mind that there is this play between both the changes in climate as well as changes in the forest cover. So we can't take everything in terms of just the change in forest cover. We have to account for the variability that occurs with current environmental conditions. But what we're seeing is that the potential can increase with deforestation or forest removal.
Perfect, thank you. So moving forward, can this project say anything about increases in blue-green algae?
I'll leave that with others. If Dr. Qi?
Yeah, I can address this question. Actually, for the water quality simulation part, I think algae actually can be simulated within the stream. But currently, this is not the focus of our project. Our project is focusing on, nitrate loading or phosphorus loading, mainly from the fertilizer application. But definitely, SWAT model can simulate blue algae or other related variables. If we can, generate the data from the SWAT model, we definitely can incorporate those simulations to the decision support system. And afterwards, we can apply the decision support system to predict, the BMP effects or land use change effects on, algae growth or die-off processes. I think it's doable, but it's not our priority right now. Thank you.
Thank you, Dr. Qi. So a question from Simon Mitchell. The Federal Environment Commissioner just put out a review of water quality in 3 basins across the country, including the Wolastoq. I'm wondering if you have any comments on some of the gaps around data, water quality, etc., that was flagged in the report and linked with a number of federal and provincial agencies.
I guess you're looking at me. I'm not familiar with that report. It would be interesting to have a look at it. We tried to supplement some of the missing data. If it's sometimes to use by using models, and so sometimes we will merge observation or observational data with simulated data to compensate for missing information. But in terms of the federal environment report that you're referring to, I'm not familiar with it.
Thank you, Dr. Bourque. We have a question from Daniel. In a study of future stream flow attributed to atmosphere land cover interaction, would you suggest the statistical downscaling of the regional climate model for generated data? If yes, and why?
Let me see. I guess I'll respond to this. In a study modeling future stream flow attribution or attribute atmosphere land cover, would you suggest? Yes, there's different ways to approaching downscaling. As Ahmed had talked about, he's using dynamic downscaling. We can also use that for future because what we get from the regional climate model is the boundary conditions. Then we can drive the regional climate model to come up with a downscaling. In terms of statistical downscaling, you could still approach it, but you need to make sure that you specify the elements of the method, either using global climate model, because you have to look at future conditions, and proceed using statistical method to achieve the downscaling that you would be interested in getting. But in terms of your question, you say land cover interaction, would you suggest the statistical downscaling data as yeah, okay, so I answered the question.
Thank you, Dr. Bourque. And I believe this next one is also for you. It's from James. It's right below Daniel's question. Can we say something about extreme weather and an adaptation of increasing forest cover to ameliorate the effects of those extreme events?
Right now we can't, but that's a very good scientific avenue to research. And I think we can do that with numerical models. So the empirical study I'm showing or showed relates to what we have experienced in the last 17, 20 years to 40 years, depending on the part of the presentation. But in terms of addressing the future, we are probably best to use the regional climate model or even models like what Dr. Qi talked about at resolutions that are probably more pertinent to the levels that most people operate at. So resolutions of let's say 100 meters to maybe 200 meters. But I think it's captured in the numerical models to do something that you talk about.
Thank you. Another question here from Daniel. From your results of the empirical statistical assessments and regional modeling of the Upper Wolastoq Basin, do you see a possible increase in discharge rate in the future under RCP 2.6 and 4.5 emission scenarios?
Well, in terms of the what I show using historical data, especially over the short term, talking about the near to maybe intermediate future, if the tendencies are somewhat what we have now, then sure, the results show that. But in terms of the long term, where there's a shift, potentially a shift in the precipitation regime. Currently, the precipitation regime is snow. With future warming, that regime will change to mostly rain. And so the relationships that we're talking about might be completely different because snow acts as a reservoir. It responds, accumulates and responds in terms of increasing discharge in the spring. With rain, that's not the case. There's no storage. And so we end up with completely different discharge regimes. And so you have to be careful in terms of how you use the historical data because it represents, our immediate past, and it doesn't necessarily represent the future. So in terms of 2.6 is a less aggressive scenario, and 4.5 to 8.5, you're going up the scale to more aggressive scenarios, and it would be interesting to see what those differences are. And of course, it would be related to the level of heating. So when you go from a 2.6 to 8.5, which is really the trajectory that we're probably following now, the rate of heating and the timing will be somewhat different. And so what does that mean with respect to shifting from a snow-dominated system to a rain-dominated system?
Thank you, Dr. Bourque. If we don't have any more questions, I would like to ask a question, if that's okay, from each of our presenters today. So as we look closer to wrapping up the webinar today, if you can answer this one question for me, if there's one thing to take away from this webinar, what would it be? So if I could have each presenter answer that question, that'd be amazing.
Yeah, the takeaway, I hope I was able to address relates to the role that force removal has on water discharge. In the literature, depending on the watershed characteristics, the literature is quite inconsistent in terms of the relationship between the environmental attributes and water discharge. but in terms of the what we see in the upper Wolastoq Basin, it's quite clear, at least to me, that the force removal has an impact by causing water discharge rates to increase, given the right meteorological conditions. For example, lots of snow and such things like that. If there's a drop in snow, of course, there would be a corresponding drop in the water discharge, given that the land cover hadn't been changed. If it's changed, then the two are working together or possibly against each other, and you end up with variation that you may not have expected.
So yeah, so the takeaway from this seminar for me, I think is the need for a decision support system. I think this is quite important for our audience, and especially for stakeholders and the decision makers. And as I talked in the presentation, a decision support system is quite easy to use tool for non-experts, and also it can also provide accurate, reasonable results, and to assess, BMP implementation and land use change. So I think there's a need for that tool, and in this project, hopefully, we can continue to develop the decision support system, and we will improve the simulation accuracy, especially with the new techniques from machine learning. Another important part from this project, I think, is to we can develop interface for the decision support system. With interface, we can share with the audience and share with stakeholders and decision makers, and make the the tool useful. But currently, we just use it as a scientific research tool. But definitely, we are working on that, and hopefully, in this course of the project, we can provide a useful tool for you guys to use.
My takeaway is not a conclusion, it is a question. Can we use the presented facts and the presented conclusion to be a tool to resist ongoing destroying of our forests, or we just only we have to present this result to decision maker and the policy maker and just sit back and see how they are going to do? Do we have any kind of responsibility, or can we do anything to prevent this to continue? This is my takeaway question after these presentations.
Awesome. Thanks so much. Again, to all of our presenters and everyone who participated in this webinar today. Again, we are going to be sending out a survey by the end of this week to get your feedback on how this webinar went. And if you think of any more questions to the presenters later, because I know that always happens, feel free to just insert that into the survey, and we will forward them on to the presenters here today. Again, thank you to everyone who came and watched this webinar today.
Yes, thank you.
Right.
Thank you.
Thank you all. Thank you.
All right. Have a good afternoon, everyone.
You too. Thank you. Thank you, Dennis. Thank you.
Bye-bye.
Bye.